Let's look at 6.3c, geometric distributions. All right, so this is a new distribution. So we've done normal distribution and binomial distribution. Now we're doing geometric. So a geometric setting arises when we perform independent trials of the same chance process and record a number of trials it takes to get one success. So until you get a success. Remember how we circled that word until? On each trial, the probability P of success must be the same. So the difference between probability and geometric is no set number of trials. We are finding out how many trials it'll take to get one success. The number of trials y that it takes to get a success in a geometric setting is a random variable. So we're calling this random variable y. So instead of saying x, it's y. Which on the formula chart, it actually still has it as x. The probability distribution of y is a geometric distribution with the parameters. P is a probability of success on any trial. So that's all we're going to be asked for when we go to geometric distribution. So our possible y values would be whole numbers, starting with 0, 0, 1, 2, 3. So this is the number of trials before a success. In the board game Monopoly, one way to get out of jail is to roll doubles. Suppose that a player has to stay in jail until he or she rolls doubles. The probability of rolling doubles is 1/6. Explain why this is a geometric setting. Y is the number of rolls until player rolls doubles. Because it says, suppose that player has to stay in jail until he or she rolls doubles. So we are going to count up how many times it will take to get the doubles. Okay, so let's check bins. B is success, is doubles. Fail is not doubles. That is binary. That is the B. I, each roll is independent. Yes, each roll is independent. Notice that there's not an N here because N is number of trials, but this says until they roll doubles. So we don't have an N value. And then S, probability of success, is 1/6 of the time. Okay, define the geometric random variable and state its distribution. Y is a geometric random variable with a probability of success of 1/6. Okay. All right, so let's look at this example. Define the geometric random variable. It says, find the probability that it takes exactly 3 rolls to get out of jail. So we do need to specify what we're looking for. Y is the number of rolls until player rolls doubles. So find the probability that it takes exactly 3 rolls to get out of jail. So Y equals 3. So that would look like fail, success. Okay, remember success is rolling doubles. Fail is not rolling doubles. So we have 5/6 because that's the complement of rolling doubles times 5/6 times 1/6. So that would be 5/6 squared times 1/6, which gives us 0.116. Okay, what about if we want to find the probability of exactly 4 rolls until we get a double? So we would say probability Y equals 4. So it would be fail, success. So that'd be fail, and then a success here. So we have 5/6 to the third times 1/6, which gives us this value right here. All right, what about 100 rolls? We would have to write this fail, 99 times, and then 1 success. So that would look like this. 5/6 to the 99 is 1/6 times 1/6 is 2.42 e to the negative 10. You never write this though. we would want to approximate this as 0.00, because this is 9 places to the left, which would be a lot of zeros. So we're going to approximate it to be a 0. So probability is most certainly not going to happen. Okay, so our formula is p minus 1 times the number of trials minus 1 times probability of success. That is the formula. And that is found on our formula chart. Okay, so that shows you the 5, 6 is the p minus 1, which is a complement of success, and then 1, 6 is success. Hey, in general, how can you calculate geometric probabilities? Is this formula on the chart? I just talked about that. Here is exactly how it's written. Actually, it says x instead, but x and k are interchangeable there. So that is our formula. In the calculator, we're going to do geometric PDF, 1 over x equals k. So we would just need p and k. CDF is cumulative, so it's everything to the left, so it's less than k. And then we can also do this in the calculator, in Desmos. Let me show you where it is found on Desmos. So you'd go here, you'd go to inference. We would need to go to geometric distribution, probability of success. So let's say it is 1/6, like our Monopoly. And so that is what it looks like. Pretty cool. So probability of each one. Earlier we found 3. Remember 3 up top, 0.116, and then we found 4. Hold on, there's 4. Okay. And then if you want to find the cumulative, you'd of course do this and specify which direction you want to go. Okay, take that away. So in general, how do you calculate the mean of a geometric distribution? So this is also on the formula chart. So it is expected value of y is just 1 over p, expected number of trials required to get first success. So yes, it is on the formula chart. Okay, so on average, how many rolls should it take to escape jail in Monopoly? Remember, the probability of rolling doubles is 1/6. So we would do 1 over 1/6, which is 1 over p, which is 6. So 6 is our mean number of rolls. Sounds like a lot. You're going to have to sit out 6 times to finally get that, to get back in the game, because you'll be sitting in jail. Okay, so what is the probability it takes longer than the average to escape jail? Oh, here is the interpretation. Forgot about that. On average, it will take approximately 6 rolls to get out of jail in Monopoly. Okay, let's go ahead and look at this last one. What is the probability it takes longer than average to escape jail? So longer than average would mean greater than 6. So if we want to do this in the calculator, we'd have to do 1 minus probability. Y is less than or equal to 6. And so we'd have to put that in the calculator. So it would be 1 minus geometric CDF of that, which gets that. Or we could put it into Desmos. So we have the 1/6, and we want it to be greater than 6. So I'm going to go to the right, and I'm going to put 6. But it says longer than average. So 6 is average, so I actually want to take that to 7. Okay, so it's 0.334, which is the same. Okay, and then another question here says, what does the probability tell you about the shape of this distribution? So look at the shape. Oh. So we can use Desmos to kind of give us an idea of what the shape looks like. So we know it's right skewed, but also using this, we want to use that. So let's see. This tells us that it's skewed right, has a tail on the right. The mean is right here, gives us 33%, but the median or the center is going to be right here. So that's how we know it's right skewed. So what does this probably tell you? That longer than average? Since only 33%, only about 33% of the data is above the mean, this strongly suggests the distribution is right skewed. That's what it tells us. Because the mean chases the tail right here. In geometric distributions, you're going to find that they are right skewed. Another thing I want you to notice about the Desmos right here is that it says geodist. Anytime we did the other ones, it said like normal distribution, binomial distribution, but this one you should write geo. But an easier way is just go inference, probability distribution, and then you choose normal, binomial, or geometric. All right. And that is it for chapter 6 notes.